I was glad to have the opportunity to read this paper, and I'm going to try to discuss it. Good. I'll do my best. There's turns out two obstacles to my discussion today. The first is that you've already seen the paper's hard. It's quite technical, and so that's why I wrote down this little oath I'm promising. My goal here is to make sure I don't at least add any confusion. But also, the other aspect is I received a new version of the paper, a dramatically changed version, Monday night. Now, I haven't had a lot of time since then to put into my discussion, and so we'll see how well my discussion slides align with what you just saw. Okay, so here's the idea. The idea, I think, is well, the environment, I think, is quite interesting, and it's certainly worth studying. So these authors, they want to think about economies that present as nonlinear systems, nonlinear dynamic systems, and they're interested in the multiple equilibria that present there. We know there's lots of different kinds of equilibria in these kinds of models, and so their goal is to provide a refinement. The idea of this refinement is going to be based on perturbations. Hopefully, the refinement will select some of the equilibria, dispense with others, and the equilibria that survive the selection process then could be viewed in some sense as being robust. So that's what we're kind of looking for here. Let's see now if I can figure out the red light. Good. So this is the model they present, and it is a non-stochastic model. Of course, we know that models like this, they may have stochastic solutions. So for example, if this model has a non-stochastic steady state that's indeterminate, then there'll be many sunspot solutions local to that steady state. Now in general, I guess it would help to have my glasses on. In general, G is not invertible. And so if G is not invertible, it's not straightforward to write down a dynamic system that moves forward in time and provides you a perfect four-set equilibrium, which is a great kind of equilibrium to be studying here. Instead, it is common that F is invertible, and so that's what they think about, and they think about then the backward perfect foresight map that comes from inverting F, and they call it phi. And so they're going to study the dynamic system then that's given by the xt equals phi, xt plus 1. And then a natural example of this is an overlapping generations model. You saw it just there at the end of the talk. I think of Grandmal as the first one to really emphasize the kinds of complex dynamics that arise from backward perfect foresight maps and overlapping generations models. But I don't know the literature that well, so don't call me on that. Okay, so what do we know about these kinds of systems? Well, we know that these backward perfect foresight maps may present cycles, or they also may present, or they may exhibit, the label I'm using here is ergodic chaos. So the idea here is that the perfect foresight equilibria that are determined by these this backward perfect foresight map may be quite complex in nature. And here's kind of how that arises. So in this latter case, when the dynamics exhibit chaotic behavior, there's going to be a set, a large meaning it has positive Lebesgue measure. And the perfect foresight equilibria that live on this set, they're going to be chaotic. They're going to dance around in quite a complex fashion. Furthermore, there's going to be a measure, another measure, this BRS, I can't remember, measure associated to that large set. And the measure that's associated to it then actually captures the mixing nature, the randomness of this perfect foresight equilibria, in the sense that the amount of time a particular perfect foresight trajectory spends in any particular region being a Borel set, is captured by the measure, this invariant measure that's associated to it. So it's very nice, and that comes from the theory of nonlinear dynamics. Now, the version of the paper I read didn't have much about, it had a little bit about these sunspot equilibria, but I had to go back and read this paper by Araujo and Maldonado. And that was a real treat. That's an excellent paper, Economic Theory 2000. And what they do in that paper is they take a system just like we saw here and consider the case where there's ergodic chaos, and they build a sunspot equilibrium associated to this large invariant set. And actually, so our speaker gave you much more of a description about that sunspot equilibrium than was provided in the paper. But I like it so much that I want to emphasize it maybe a little bit more. So this first bullet here, well, that's just how I described what happens when the backward perfect foresight map exhibits ergodic chaos. And then they build this transition dynamic. He actually wrote the transition dynamic on the board for you, but on the screen for you. But I want to give you, I'm not going to talk through the details, but I want to give you a sense of how intuitive it is. So this is just the transition function that goes along with the Markov process that's capturing this sunspot equilibrium. This is just measuring the probability of moving from some point X to some set B. And how do you intuitively think about this funny thing on the right? Well, all you do is you think about moving back along any perfect foresight equilibrium that exists on this set, any one you want, and just count how many times you moved from X to B. That's really the empirical distribution that goes along with a particular perfect foresight equilibrium, but that empirical distribution then asymptotes to the true invariant distribution, which is labeled mu. So I think it's a really nice idea for constructing a sunspot equilibrium, and the interesting thing about this sunspot equilibrium is that its invariant measure corresponds to the invariant measure of the dynamic system that wasn't stochastic. And finally, it is a truly stochastic equilibrium, even though it comes from or arises naturally from a model that's deterministic in nature. So I think that's you didn't just put a 5 up, did you?
No, really.
Okay, really? That doesn't sound fair. Okay, and so what they propose to do is to, remember we had technical difficulties. What they propose to do then is to try to define a refinement notion associated to these complex equilibria. And here's their refinement notion, and he put it on the board. Now, I put in what turns out to be not pink, it's magenta, the term that's being defined here. So one of my recommendations is you got to get a catchier term, because I'm never going to remember a small deviation. Anyway, you can read it yourself. That's the term that's being defined, and it's this process X tilde. And as you saw, his idea, or their idea, is to take this shock process, which has small support, send it to 0, and see if this stochastic process, determined by this dynamic system, in some sense converges to one of the equilibria of interest. So here's the interpretation that's provided from the paper. I think it's useful for us to read through these together, because like many of the people in the audience who were asking questions, I was struggling a bit with how natural that dynamic system was to associate to a model that was deterministic, comes from a backward perfect foresight map. So here's what the authors say. They say, given the actual value next period, the actual value is xt tilde. Well, this is what should, in a sense, rationalize tomorrow. Phi of xt tilde. That's just the backward perfect foresight map. And then you can read this yourselves, but for a variety of reasons, they say that's not the one you're going to observe. This is the important bullet, I think. The actual state variable that rationalizes x tilde t plus 1 is xt tilde, which is this stochastic perturbation of phi of xt tilde plus 1. So this is the justification the authors provide for studying this stochastic process. And that's really, that's going to be my point of critique. I'm not sure I fully understand why that's a natural object to study. But I'll come back to it. But for now, we'll give it to them. And then they have one more definition. And again, I put in magenta the term that's being defined. But essentially, it's just like you saw from the top. We're going to say any particular equilibrium is selected by their mechanism if the stationary measure associated to that equilibrium is what's reached when you send the supports of the perturbation to 0. Okay? And then their goal is to identify which of the equilibria in this model are selected by their mechanism. And they have their main result has changed. This is the main result that was in the first paper, and it's still at the heart of the second paper. And I think the idea is quite natural. Here's the idea. Suppose, so this is how people like me punt on things. Suppose the backward perfect foresight map is nice, and suppose this is just the density functions for the stochastic shock. Suppose they're both nice. Well, then it turns out this perturbed process has a stationary distribution associated to it. We'll call it nu epsilon. And two things are true. First, as you send epsilon to 0, nu epsilon converges to the invariant distribution. So I want you in your heads, by the way, to be thinking we're in the ergodic chaos case. That's the one that I'm going to focus on. So as epsilon goes to 0, these measures converge to the invariant measure in the ergodic case. And furthermore, this is just the sample distribution along any particular realization, and you get convergence of the sample distribution to the mu as well. So, this is their central theorem, and this is the theorem that they're going to take as providing the selection. So it's going to be that when phi and theta epsilon are nice, this selection mechanism is going to select the equilibria that have the associated stationary distributions. So here are the implications that they take from this. They say, we again look at the case of ergodic chaos, the perfect four-side equilibria, the chaotic perfect four-side equilibria, and the sunspot equilibrium, the unique sunspot equilibrium, they're the equilibria that are selected because they're the ones that have as an invariant measure this mu. The second bullet is actually the one that I think is maybe the most important part of this theorem, and it says that if you take any particular perfect four-side map and perturb it stochastically a little bit, the stationary measure isn't going to be very far away from mu. So there's a sense in which, this is what I think of as the robustest result. Mu is probably a pretty reasonable object to study. That's one that comes out of the model, because if you got it a little bit wrong, the invariant distribution is close to mu. Now, two. So let me then get to the one concern I have, and I think it's best questioned within the context of a model. This is exactly the model that he studied. The only distinction is I have an agent-specific indicator here, because they're really kind of, at least in the paper that I read, they focused on coordination issues, and so I was thinking about heterogeneity. But this is just an overlapping generations model with money and labor endowments into each period. And the variable of interest is Q. That's the goods price of money. They had written it as P inverse. Okay? Completely standard. Don't have time to solve the model for you, but you've done this many times yourselves. If you assume rationality, you get exactly the dynamic system they're interested in studying. If you think about it, if you back away from the assumption that agents are rational, instead each agent is forming forecasts somehow, so there's some sort of lack of coordination, there's some sort of error, something like this, then the equilibrium really arises from a situation that looks something like this. This is money market clearing, and this is the money demand of a particular agent. So if I go to the next page, this sort of outlines the concern I have. What I really want to understand is why this is a reasonable object of interest. And the way I think I could do it would be to see that this dynamic system comes from some way of thinking of agent behavior within the model arising from equilibrium in the money markets. So for example, if agents had perfect foresight, this is how price today would be determined. We would have, this would be under homogeneity. And so under homogeneity, let's see, they would have belief that tomorrow is QT plus 1, and they would act in a way so that the realization today is QT. That's what we started with. Now suppose we have homogeneity, but now agents aren't perfectly rational. There's some sort of disturbance or distortion. Well, then they're forecasting expectations of this thing somehow, and then they're acting in some way, and we get the realization of the price today. What I'd like to know is how I could somehow take these two and get to this map. What kind of errors are they making? How are they forming expectations? How is it we move from a system like this to the system that they're studying? And if I understood that better, then I think I would know how natural this dynamic system is. I had a few more thoughts concerning how to do adaptive learning in this model, but I'm out of time. And so just conclude that I think it was an interesting paper with an interesting refinement notion, and I'd like to really study it more within the context of a particular model. Okay, thanks.